Thank you. So my name is Nishant Mishra. I'm a third-year graduate student at University of Michigan, working with Sean Johnson. Survey specifically studying dwarf galaxies with respect to O6 absorption. So first, I'd like to thank some of the collaborators, including Gwen Rudy at Carnegie, Xiaowen Chen, who is here today from Chicago, Yop Shea, Zijie Q, and Fari Zahedi, and many of the others in the Cubs collaboration. All right, so Michael was nice enough to do some of my introduction for me. So why do we study the CGM of dwarf galaxies? Well, as he mentioned, they're very, very sensitive to feedback due to their shallow potential wells. And you can see that through the mass-metallicity relation, where we find that the lower mass galaxies are, in general, more metal poor. And so the story goes that some of those metals must be deposited into the CGM or even further to the IGM. And so this is kind of another example of that, showing a simulation from Mina et al. 2021, which shows two different feedback prescriptions. And it shows that the metal column density for both of these feedback prescriptions for the same galaxy is wildly different, including the extent of the metals out into the IGM, even going out to upwards of megaparsecs. Okay, so there's a few challenges associated with observing dwarf galaxies. So first is they're very, very low luminosity. So on the left, you have a local dwarf galaxy of stellar mass of 10 to the 7 or so. You can see it's easily visible. And so this is an image from our survey. And one of them is the dwarf galaxy that I'm going to talk about. And if you can't see it, it's because it's very hard to see. It's that one right there below the quasar. And it's of a similar mass, but the kind of problem is that it's at intermediate redshift, right? It's a redshift of 0.7. So the question you might ask is, okay, why do we need to do this? We have a nice galaxy right there. It's kind of the same thing. It turned out that it's related to the ions we want to observe and what we can learn from those ions. So it turns out that local dwarf surveys lack some of the ion coverage of many of the ions that we're interested in. So in particular, oxygen-6, as you can see, only enters the redshift range or the spectrograph range of HST COS around redshift of 0.1. And H1 is also inhibited because of the width of the Milky Way's H1 absorption. And so it means that we need to go to intermediate redshifts in order to get access to O6 and H1, which are the most common ions in general that are observed in absorption spectra. Okay, so a second challenge, as was pointed out by Chris kind of in his talk, is that environment is very important, right? So if we have a dwarf galaxy that might be a satellite of a much larger dwarf galaxy, or much larger galaxy, you would expect that they're susceptible to many of the environmental effects associated with being a satellite. Right? So this is a simulation paper from Zhu et al. 2024, which is basically a kind of a wind tunnel simulation where you create a dwarf galaxy with a multi-phase CGM, and then you kind of turn on this wind, kind of equivalent of the galaxy going around a Milky Way mass halo, and you find that the Milky Way, the CGM of that dwarf galaxy is very easily stripped off, right? And so it means that if we want to study the CGM of dwarf galaxies, we want isolated, oh dear. Oh, not the update thing. Skip these. Oh my God. Yeah. Can we go back? Oh, okay. Cool. So as we mentioned, the CGM is easily stripped. Okay. So that's where our survey, Cubs, goes in. So I won't cover too much detail. I'm sure Xiaowen will cover in much more detail because she wrote the kind of first paper about the survey. And so our survey is well positioned to kind of answer these questions, primarily because it is structured in what we call like a wedding cake structure. So the inner part of the survey, nearer to the quasar sightline, is very, very deep, which allows us to access those dwarf galaxies and observe them and get precise redshifts. And then the outer parts of the survey help us get access to a wide range further out from the dwarf galaxy and allow us to characterize the environment. So we can easily tell, or confidently tell, whether a galaxy or dwarf galaxy is a satellite or a field dwarf galaxy. Okay, so from there we move on to our sample selection. So we want dwarf galaxies, so we select all galaxies with a stellar mass below 10 to the 9, and we isolate them against galaxies that have a stellar mass above 10 to the 9. And we isolate to 500 kilometers per second in velocity space and half a megaparsec in angular distance. So the kind of previous work on this sort of work at intermediate redshift was done by Sean in 2017, and so the number of galaxies was around 11, going up to a redshift of 0.3, and so we bumped that up considerably, and so to a factor of 9, and now we have around 100 galaxies, and we go out to a redshift of 0.77. We cut that off at 0.77 because that's when O6 leaves the spectrograph range of COS. Great. So from this, we just do void particle fitting and kind of infer the column densities. So we found that in general, there's strong absorption stronger H1 absorption near the galaxy, and it gets weaker as you go to larger impact parameters, and the covering fractions also drop. In general, for lower ions like carbon-3, we find limited detections and basically no absorption outside the virial radius. So this is in contrast to oxygen-6, which is by far the most common ion, and extends, kind of importantly, extends beyond the virial radius. And so what that suggests is that a significant portion of the O6-bearing mass is actually contained outside the virial radius. And so we kind of do a pretty simple order of magnitude calculation to kind of calculate what fraction of the O6 mass is contained outside the virial radius. And so we find that it's pretty equal. We find that the first bin, which is 0 to 1, is of order of magnitude similar in mass to the second bin. And that dotted line at the top is actually the mass inferred by Milky Way-like galaxies, which means that if you look at the total mass associated with dwarf galaxies' O6-bearing mass, it's actually pretty similar, which implies that the fraction of gas that is O6-bearing in dwarf galaxies is significantly higher than it would be in Milky Way mass galaxies. And then secondly, the inferred mass so we take the upper limits from all of from the third bin and we stack them and give us an upper limit on the mass in the third bin, implying that even after you go to the second to virial radii, the drop-off is quite steep. And so the conclusion is that the CGM and the nearby IGM are substantial metal and baryon repositories. Okay, let's move on to the kinematics. So after we do void profile fitting, we can ask what is the distribution of the kinematic distribution of the absorbers associated with these dwarf galaxies. And so we quantify this using what's called formally, using a term we denoted formally unbound. So it's what fraction of the galaxies contain absorbers that are outside the escape velocity of an NFW profile of that mass, galaxy mass. And we find that around 15% of galaxies show formally unbound metal absorption. So this is actually an agreement with for a similar redshift for Milky Way mass galaxies. But if you go to higher redshift, you find the unbound fraction is actually significantly higher, suggesting that the kinematic structure of the O6-bearing CGM is different at higher redshift than it is at low redshift. Okay, actually skip through the introduction because it was already done for me. So I'll go ahead and go through my conclusion. So we studied isolated star-forming galaxies with stellar masses of 6.7 to 9. We commonly observe H1 and O6 at a range of projected distances. The inferred CGM mass is comparable to those of Milky Way mass galaxies and actually exceeds the stellar mass and the expected 21 centimeter mass. And the kinematic distribution of metal absorbers is similar to that of Milky Way mass galaxies, but is narrower than that of galaxies at redshift 2. And then so the next steps are using photoionization modeling to get metallicity estimates, comparison to simulations, so like Michael simulations. And then we're actually taking near UV spectra using STIS as we speak, so we can get carbon-4 to compare with oxygen-6 in the hopes of kind of doing some of the BPT type analysis that was discussed earlier in the conference. Thanks.
Any questions? Yes.
So in your data, is oxygen-6 the best metal line, or do you have other metal lines that are more prominent for these galaxies?
In general, O6 is the best metal line. We found a few carbon-4s, but carbon-4 leaves the range of the spectra pretty quickly. And so I think we're waiting for the STIS spectra, and then we'll go back to these galaxies in the STIS spectra at some of the higher redshifts to see that we can get some carbon-4 absorption. But yeah.
Just to follow up, like mostly the hot ions are the better.
Yeah, in general.
Yeah.
Yeah, I'm curious about if you've looked at the width of the O6 spectral lines to try and get some handle on the temperature as you're moving into these like lower mass halos, if O6 is moving into cooler and cooler gas.
Yeah, so the temperature for O6 is kind of challenging. So for lower ions, you can tie the ions together with H1, and then you can separate the turbulent width from the thermal width. But when you're at O6, it's usually kinematically structured differently than H1 or something like that. So you would need another high ion to be able to tie it. So that's where carbon-4 comes in, because then you can constrain the turbulent temperature, turbulent width versus the thermal width, and actually get a temperature constraint.
Yeah, Jeff.
Yeah, so first of all, congratulations for extending this to 100 galaxies in this mass range. This is a very impressive data set. And I appreciate how hard it is to get this sample, so very well done. When I first made that kinematics plot for the Costello's data set, like 10 years ago now, it just kind of blew my mind that all the O6 was effectively bound, because we were, even then in those days, still trying to prove that all this stuff was really associated with the galaxy. So, and I know you're not there yet with assembling all the ions, but it's a really important question whether you see this boundary where the O6 drops below your detection because you run out of metals or you run out of gas at that ionization state. Any insights to that yet?
I'm not sure what the exact question is, but
Well, in your O6 column density plot, right?
let's go back.
You reach a point where it goes from, meaning it goes, at 2 RVR it goes from, you have 2 detections out there, mostly upper limits, and then beyond there you have mostly upper limits, right?
Yeah.
So that's the boundary of the detected O6 region. And we're still trying to answer the question, I think, of whether that is caused by the metals becoming less common, and therefore that has implications for chemical enrichment, or the ionization state of the gas changes.
Yeah, so I think we also don't see anything in low ionization state, so I think you'd have to look at like higher ionization, maybe eats up further, but yeah. We don't find any detections of low ions either. So we also did stacking, so we also found that it's definitely not there, even in the stack. And the drop off is pretty steep. So yeah, I hope that kind of answers your question.
Just one quick comment. So that's really always the hard part. You cannot rely on UV ions alone. I think that's where, if we have deep X-ray observations to come in to help provide some insight on 07, 08, that would be really helpful.
Yeah.
So right now, based on available transitions, this is it. We also search for neon A, but neon A is just really a hard transition to detect.
Do we have any more questions? Yeah, one more.
Yeah, I noticed that your stellar mass range went down to 6.7. Do you know your your O6 columns? Did you detect O6 around like that low mass galaxy, or was more?
10 minutes. I think the low. You mean that one right there in the back corner?
Yes.
I don't think we found O6 there, but I think, for example, that big one right there at the top, like almost near 10 to the 15, that is like a 10 to the 7 something galaxy. So, yeah.
All right, let's thank Nishant and all our speakers.